Okay, so let's do this example. It is kind of similar to the last example that we did, but it's slightly different. Why? Because this power series needs to be centered at the origin. Okay, so let's see here. So we have f of x is equal to natural log of x minus 1, and that is the same as, or that implies that f prime of x is going to be 1 over x minus 1. Hey, we know exactly what this is, right? This is the same thing as negative 1 over 1 minus x. And so f prime of x is negative 1 over 1 minus x. But that's just the sum x to the n equals 0 to infinity. And I need to account for this negatives. Okay, so I'm going to put a negative out here. Okay, and this is valid when x is in between 1 and negative 1. So that's just our original geometric series. So what does this mean for us? So if f prime of x is equal to the sum, now we can just bring this negative right on the inside, of negative x to the n on negative 1 comma 1, then f of x is going to be the antiderivative of its derivative, right? That's why it's called antiderivative. And that is by the fundamental theorem of calculus. So we'll have the integral of f prime of x dx. Now what is the integral? So now we have the integral of the sum from 0 to infinity, negative x to the n dx. Okay? And so this is like negative 1 times x to the n. So everybody get that? So the first thing we can do is we can interchange the integral and the summation sign. Okay, so now when we interchange that, we will get the sum of the integral of negative 1 times x to the n dx. And now it's like the focus is really on this part in here. Right, so it's almost as if you're, back in Calculus 1, learning how to integrate. Okay, so we say, now what is this integral? Okay, well, first thing we would do is we would pull out this constant, so it'd be negative integral x to the n dx. And now we know the formula for this. In fact, isn't this called the power rule for derivatives or for integrals? So we know this is going to be x to the n plus 1 over n plus 1, okay? And then we'll have plus a constant. We still got that negative sign. 0 to infinity. Now we can go back and add on our summation. Now notice that we know that n, so this n right here, can't be a negative number. In particular, n can't be negative 1. So we don't have to worry about, hey, what if n equals negative 1 and really x to the n dx is equal to the integral of 1 over x dx. We don't have to worry about that because we know that this n comes from this index over here, right? So n can be 0 or any positive integer. So it is okay for us to use this as our answer. Okay? And so we can just say our final answer is negative sum x to the n plus 1 over n plus 1 plus a constant. And now where is this valid? Again, we know that the radius of convergence isn't going to be impacted. Perhaps the endpoints, but I'll leave that to you to check. So we'll have negative 1 to 1. So valid on negative 1 to 1. And then I'm leaving it up to you. At home, you should check the endpoints. Right? So you should see, is negative 1 really, does this power series converge when x equals negative 1? The answer is no, it doesn't. Does this power series converge when x is equal to 1? The answer is no, it doesn't. Okay. And similarly, you should do the same thing for the power series that we did here, right, with this example here of natural log of x centered at 1, and for the example with, oh, we did it for this one right here, right? So we did it for this first example here where we're integrating and differentiating. Our very first example of integrating and differentiating, we did it already. But so I'm going to leave that to you to check. Now, one last thing that I wanted to do was I wanted to compare the series. So what is f of x equals natural log of x, but now it's going to be centered at 1, versus f of x equals natural log of x minus 1, centered at the origin. Okay, so first let's start off with natural log of x. And we know the natural log of x goes something like that. It grows, but very, very slowly. This point here is 1, 0. Okay, so if we are centered at 1, then here's what that means. That means basically, it's like our window, what we're concerned with. And we said that, didn't we say our interval of convergence was from 0 to 2? It's not that one. Here we go. Interval of convergence was 0 to 2. Okay, so what that means is for our picture here, we're only concerned with what's happening in between 0 and 2. Okay, so in fact, I'm going to erase everything outside of here because we only care about what's happening, right, between 0 and 2. So like here's 2 and here's 0. There's an asymptote, right? And then 2, however, there's, it's got a, even though there's not an asymptote, natural log of x. Let's see here, what happens? It looks like we should be okay to define it at 2. Let's look and see what happens. If we go back to this one right here, let's see here, so this power series is centered at 1. I'm going to check very quickly. If so at x equals 2, our power series is going to be, oh no, that's not the one. We need to be down here. So at x equals 2, our power series needs to be at x equals 2. It'll be -1 to the n, and then 1 over n plus 1. Okay, so this is going to converge by the alternating series test.
It's 14 hours.
Thank you. So let's actually update this to converge here, 0 to 2. And now we know we're going to have a problem if x is equal to 0, because at x equals 0, then we'll have something that diverges by limit comparison test with the harmonic series. Okay. So this is what you should get. This should be the interval of convergence, log of x. So that's why here we can include 2, but we can't include 0 because we've got an asymptote. And on the other hand, what's happening over here, this is natural log of x minus 1 centered at 0. So now the natural log of x minus 1, how do we get that? That's just a translation of natural log of x. So we're going to shift natural log of x over by 1 unit. And so if we shift it over, we would get something like this, right? Our asymptote would shift, and we would get something that grows slowly. Let's see here. So we're shifting it. Hold on, wait. So at 1, we've got a problem. Okay. All right. Now what did we say was our domain? Because our domain can't be from, our domain can be from -1 to 1. So centered at 0. So our domain being from -1 to 1, here's what we actually have. We're going to have the absolute value of x minus 1. Because if I look at this picture and I want to look at the domain that is from -1 to 1, right, we're looking over here. So you see how here's 0, and then you have to keep going this way to get to -1. So for the natural log, you know how when you have y equals natural log of the absolute value of x, that allows you to mirror, right? It looks something like this. So you've got like that, and you've got this side right here. So that's basically kind of what we're going to need to do. So we'll have this. Now if we reimagine this, and now shift this part over, and we'll get something like, let me use my pink. We'll get something like that. Okay, and so over here, the power series, since our domain is from -1 to 1, now we're having this asymptote, and it's going to go from -1 to 1. And we're having this asymptote here. So now, let's see, it looks like it should be fine at -1, but from our computations here, it is simply not. Okay. So these are our correct endpoints, -1 to 1. And you can see kind of what happens as you are looking at transformations, translations of series, right? Scaling it up, scaling it down, right? Shifting it to the left, shifting it to the right, multiplying it by a scalar. You can get an idea of kind of what that does to the domain of the power series. Okay, so for instance, this power series was centered at the origin. Here, this was our final answer. This power series was centered at the origin, whereas the other power series was centered at 1. Okay. All right.